Picture a silent ember drifting toward the sun, moving so quickly that no gravity well in our system can bind it. That ember, provisionally tagged 3I Atlas, appeared in late June when the Atlas Hazard Survey cameras in Hawaii and South Africa logged a faint, fast intruder. Initial orbital fits showed an eccentricity greater than 1, the mathematical stamp of an origin beyond the sun's reach. We have met only 2 such emissaries before, 1I Oumuamua in 2017 and 2I and Borisov in 2019. Now a third arrives, tugging at our curiosity and our instruments in equal measure. The object's present speed is almost 70 kilometers per second, enough to span New York to London in 90 seconds. Backtracing the path leads toward the constellation Lyra. Forward projection shows a swing past Mars on 3rd October 2025, a solar perihelion 20 days later at twice Earth's distance, and final escape by early 2026. Earth stays on the sun's far side throughout, so the risk ledger reads 0. The intrigue ledger, however, is packed. Composition sits at the top of the to-do list. A comet would sprout a gaseous veil as ice evaporates, yet deep imaging has yet to reveal any coma. An asteroid would follow purely gravitational curves, yet a whisper of extra thrust may lurk in the astrometry. The James Webb Space Telescope can cut through reflected sunlight and sample the infrared glow for water, carbon monoxide, or exotic minerals. If the spectrum comes back featureless or metallic, theories multiply. Brightness fuels the puzzle. Even with a modest albedo, the observed flux implies a body several kilometers wide, far larger than Oumuamua, whose size was measured in hundreds of meters. A highly reflective hull could achieve the same luminosity with far less mass, a possibility that keeps technosignature specialists awake. Professor Avi Loeb, already known for suggesting an artificial origin for Oumuamua, is lobbying for continuous JWST tracking to test for non-gravitational acceleration. A persistent drift unaccounted for by gravity would demand explanations that push against the boundaries of conventional astrophysics. Statistics pose the second riddle. For centuries, astronomy recorded 0 interstellar passers-by. Now we count 3 in 8 years. Better sky coverage explains part of the surge, yet simulations indicate the detection rate is still high. Either the density of galactic debris is underestimated, or transient swarms are sweeping the sun's neighborhood. The Vera C. Rubin Observatory, starting full operations next year, will clarify the odds by mapping every moving speck down to faint magnitudes every few nights. Structure forms the third unknown. Light curve monitoring can reveal whether 3I spins like a platter, a spindle, or a rubble pile loosely bound by microgravity. Oumuamua's flattened shape and unexplained kick remain controversial. A repeat would strengthen calls for new physics or new engineering. Rapid tumbling might indicate past collisions, freshly exposed ice, or even deliberate attitude control. That opportunity extends well beyond the object itself. Each interstellar visitor carries isotopic fingerprints of the chemistry that shaped alien worlds. Sampling those fingerprints, even remotely, refines models of planet formation, volatile delivery, and the migration histories of giant planets. In a decade, robotic missions may be fast enough to intercept such bodies. Today, we practice with photons. Time is tight. By September 2025, the object will vanish into solar glare. By the time it re-emerges, the outbound leg will dim below major telescope thresholds. Roughly 5 months remain for the most ambitious observations. Teams are coordinating radar pings, ultraviolet spectra, and high-cadence photometry to squeeze every bit of information from the fleeting visitor. Why should the broader public care? Because 3I Atlas is a tangible reminder that our solar system is not an island, but a crossroads. Somewhere, an unknown star flung this body into the dark, perhaps through a near miss with a giant planet, perhaps through a cataclysmic collapse of a binary pair. After wandering for millions of years, it has brushed past our doorstep, offering a message in a bottle. The galaxy is bustling, and we are part of that bustle. Whether the newcomer proves to be ice, rock, metal, or something unprecedented, its brief appearance renews a sense of frontier. Sky surveys sharpen, theories adapt, curiosity deepens. The next discovery may come sooner than anyone expects, and when it does, the groundwork laid today will allow us to read its story more clearly. For now, astronomers chase a streak of light across CCD frames, and every clear night might deliver a clue that rewrites chapters on planetary science, or adds a footnote to the search for artifacts among the stars. In either case, the sky is not done surprising us. Origin scenarios abound. Some simulations eject 3I from a nascent planetary system after a close brush with a giant planet, while others invoke a crowded stellar nursery where passing stars fling debris across interstellar lanes. Whatever the trigger, the body has drifted for perhaps tens of millions of years, carrying the isotopic signature of an alien chemistry lab. Radio arrays will also listen for narrow-band emissions, more out of thoroughness than expectation. After Oumuamua, techno-signature protocols are standard. Scan, archive, move on, unless a signal repeats. Looking ahead, Rubin's legacy survey of space and time should uncover several interstellar objects every year, identified early enough to permit rapid robotic flybys. Concepts under study at multiple space agencies outline launch-on-alert missions that could sample surface dust or even return grains to Earth. Each discovery thus acts as rehearsal for the day we chase one down in person. Whether the outcome is ordinary or transformative, the chase itself pushes instruments, sharpens global teamwork, and teaches the next generation to aim beyond yesterday's limits.
Whoa! A wall of fire spreads around the epicenter of the impact. It burns everything in its path. The waves raised by the explosion cover large cities, and earthquakes are so strong that giant skyscrapers fall like a house of cards. So, these are the possible consequences of the collision with the first interstellar object in history to visit our solar system. We discovered it in 2017, but we're still not sure what it is. An asteroid, a comet, or a spaceship of some outer space civilization. So far, scientists have named it Oumuamua. Sounds like a Hawaiian cow. Well, whatever it is, its speed is much faster than other asteroids, about 54 miles per second. At that speed, you could cross the US from coast to coast in less than 3 minutes. So this asteroid could travel from Earth to the Sun in about 2 months. By comparison, our rockets can travel up to 17,000 miles per hour. The same trip across the United States would take them about 9 minutes. So many scientists speculate that this is an artificial object created by a very advanced civilization. Okay. The shape of the object supports this theory. It's long and narrow and resembles a spaceship. It's about half a mile long, way bigger than the Eiffel Tower. Scientists decided to see if Oumuamua was really someone's spaceship and pointed some radio telescopes at it. If the civilization on that ship had used communication or scanned us with their tech, we would have known about it. But there was complete silence. Kind of like that. Not a single radio wave. But that doesn't disprove the theory of outer space civilization. To find out for sure, we decided to determine the weight of the object. To do that, we use light. More precisely, its reflection. You see, different materials reflect light differently. We take an unknown black stone, for example. It absorbs almost all the light, reflecting almost nothing. Check out the catalog, it's charcoal. Knowing the size and material of the object, we can determine its weight. So, we need to see how much light this object reflects. And when scientists pointed their telescopes at Oumuamua, they learned that it reflects colors that match with iron and also with some solid rocks. And Oumuamua was flashing all the time, a bright flash. Then it would slowly fade, and then it would start to shine again. This means it was spinning. And it wasn't going around its axis like an arrow. It rotated chaotically, moving its edges up and down. Any artificial object or spacecraft would have been torn apart by such overloads. But Oumuamua is still intact. That means it's made of super hard materials that keep it from falling apart. And it's not hollow like a spaceship. It's one solid body. Hey, like me. The astounding speed of this object makes it pretty mysterious. Some comets can have the same or even higher speed, but they also have a kind of rocket effect. So when a spaceship starts from the launch pad, you see fire bursting out of its engines. Every second, the rocket mixes fuel with oxygen, ignites them, and ejects them at a tremendous speed. According to the laws of physics, this is like pushing off a wall. The rocket sort of jumps up from the combustion gases it throws down. That's how the rocket creates thrust and accelerates. Comets work on a similar principle. The sun's rays hit the surface of the comet. Light elements like ice start to evaporate. That gas goes one way, the comet goes the other. Just like a rocket, the comet is pushing off the evaporating gas and accelerates. This gas also forms the comet's long tail. It's as if the massive rock is dragging all this gas behind it. I can relate. Or it's like a car pulls air with it when it goes at high speed. But Oumuamua is not a comet, and it doesn't have that tail, and it doesn't have the same rocket effect as a comet. So it couldn't have accelerated to that speed. But some scientists believe that Oumuamua used to have a tail. Although we discovered it in 2017, it entered our solar system in 1995, and it was hit by the sun's rays even back then. When we discovered this asteroid, it had already lost about 95% of its mass. It simply evaporated. Other scientists believe that Oumuamua got this velocity during its birth, somewhere far away in another star system or nebula. Perhaps it was a dramatic collision of some exoplanet with another cosmic object. The colossal explosive energy of the collision threw the elongated shard into outer space. Or it could have been a supernova explosion. When a star reaches the end of its lifespan, it becomes a red giant. It's an inflated version of the star, hundreds of times bigger. Then it shrinks and explodes with tremendous force. The blast waves can travel many light years away from the epicenter, and it's one of the brightest events in the universe. So the supernova might have torn some exoplanet to pieces. One of them, Oumuamua, gained a lot of energy and speed and began its long journey toward Earth. This might explain why Oumuamua keeps spinning so wildly. But recently, scientists published a theory that Oumuamua may be a giant block of ice. The kind of ice we're used to is water, H2O, but Oumuamua could be nitrogen ice, N2. It may have remained intact in interstellar space for 500 million years. And when it arrived in our solar system, nitrogen ice could have reflected 2/3 of the sun's rays, so it didn't heat up as much. That explains why Oumuamua doesn't have a tail. You can find the same nitrogen ice on Pluto, as well as on Triton, one of Neptune's moons. So Oumuamua comes from a similar icy exoplanet. But we can find out for sure only by sending a space probe to it. Scientists came up with a plan for that called Project Lyra. The problem is that Oumuamua is leaving our solar system at tremendous speeds, much faster than our rockets can fly. And we need to catch up with this space rock as quickly as possible before it gets too far away. To do this, we can use a gravity maneuver. First, the space probe makes a flyby of Jupiter. It passes close to it to take advantage of its gravity to accelerate. After that, the probe will head towards the Sun, and it'll fly around it as close as possible to fire like a catapult towards the space rock. The second option for reaching the asteroid is to use microprobes. We have to launch about 1,000 of them into orbit. They should be no heavier than a match. Each of them will have a light sail the size of a boxing ring. Then we'll focus a powerful laser beam from the ground onto this sail. It will allow us to accelerate the probe to about 20% of the speed of light. It shouldn't go too fast not to fly past the asteroid. It should be able to enter its orbit or land on it. But if we're too slow, Oumuamua will leave our solar system before we can catch up with it. It'll be a great experience because in the future, we'll be able to use such asteroids as a space taxi. All we have to do is enter the orbit of such an interstellar asteroid or even land on it. Then we would keep moving through space at incredible speeds without using any fuel at all. This would be a great option for traveling long distances or to deliver supplies to other star systems. So why should we be afraid of such objects? Well, a collision with an asteroid the size of Oumuamua could wipe out an entire state. If it were to hit somewhere in the ocean, it could cause waves taller than our skyscrapers. Scientists are anxious to find ways to protect us against such objects. One of them is ramming. If we spot a potentially hazardous object, we could send a spaceship towards it, pedal to the metal. The spacecraft will have to ram the asteroid at an angle that will move its trajectory just a little bit. Moving it too much on a cosmic scale would only dramatically change the asteroid's final destination, and we only need to get the asteroid past our planet. We can also create a controlled explosion on the asteroid. It's based on the same principle. the force of the explosion would have to shift the trajectory of the asteroid slightly, or smash a giant rock into smaller pieces. Asteroids up to 80 feet wide would burn up completely in our atmosphere due to friction against the air. Rocks between 80 feet and half a mile in size may not burn up completely and cause local damage. Anything larger is considered very hazardous. You think? The traditional method of science fiction is to put rocket engines on the asteroid. Then we can not only change the trajectory of the space rock, but also control it. And we can use it against other asteroids. It would be something like space billiards. Alright, so our universe is four-dimensional. 3 dimensions are for space and 1 is for time. Now let's mix them together. We're getting a nice dough called space-time. This dough has one amazing feature. Even though you can't use it to bake a pie, you can bend and tear it. Now forget about our culinary analogy. We're going to space. Waves traveling through space-time can travel at speeds much greater than the speed of light. Now, when it comes to propulsion, or simply put, moving forward, traveling through space by ejecting hot gas from the back of your spacecraft is not the most efficient approach. But a much more elegant way is to manipulate the fabric of space-time around your ship. That's how we get to the topic of the Alcubierre warp drive. So far, it's just a hypothetical concept, but who knows? Maybe in 10 or 20 decades, we'll use this device to visit our relatives who have moved to the other side of the Milky Way. Anyway, the warp drive theoretically contracts the space-time in front of a spacecraft, simultaneously expanding the space-time behind it. It allows the ship to move from one point to another at an insanely fast speed. While the spacecraft would be distorting space-time, someone outside the ship's warp bubble would observe it moving faster than the speed of light. At the same time, if you were that lucky traveler inside the ship, you'd feel no acceleration whatsoever. If we could make such a superluminal warp drive a reality, superluminal, which is a fancy word to describe something faster than the speed of light, it would change our lives for good. It would enable us to travel all over our solar system and perhaps help us reach neighboring star systems as well. For example, we could get to Alpha Centauri, the closest to a star system located a bit more than 4 light-years away, within days or weeks instead of thousands of years. Unfortunately, I gotta quench your enthusiasm, my friend. The warp drive has a huge problem. The force behind its operation, which is called negative energy, involves pretty exotic particles. Even worse, they're completely hypothetical, and as far as we know, don't exist in our universe. Scientists have only managed to describe them in mathematical terms. These exotic particles behave in unexpected ways. For example, they have negative mass. Boy, I wish I could pull such a trick after a big family dinner. And they work in opposition to gravity. But wait, there's still some hope left. A new discovery might solve this seemingly unmovable roadblock. Researchers from New York City have envisioned a positive energy system that does not mess with the known laws of physics. The authors of the study claim that it's a game changer and could be the first chapter in the manual for interstellar travel. You see, this positive energy makes all the difference. Now let's say you're an astronaut on a spacewalk and you decide to play tennis out there. So you push the ball away from you. But instead of floating away, the ball pushes back. And this confrontation can continue to the point that it might take your hand off if you apply enough force. Now that's a quality of the negative energy the warp drive needs. But as you can see, there's no way to harness this energy, and it sounds rather dangerous. That's why we should probably turn to good old positive energy for the construction of the warp bubble. This bubble is a spherical structure surrounding a spacecraft using a shell of regular, albeit super dense, matter. The bubble propels the spacecraft forward using the powerful gravity of the shell. But the passengers inside the ship don't feel any acceleration. An elevator ride is apparently more eventful than hurtling through space in such a bubble. All because of the immense density of the shell and the pressure it would exert on the interior if controlled properly. And since nothing can travel faster than the speed of light, according to the theory of general relativity, The bubble is designed in a way that those inside could experience normal time. At the same time, the bubble compresses the space-time in front of it and expands it behind the ship, just like that warp drive that uses negative energy. It allows it to ferry itself and the craft unbelievably fast. The walls of the bubble produce the necessary momentum, just like the momentum of balls rolling. If you decided to take up the task of controlling a warp bubble, it would require a great deal of coordination. Such bubbles need enormous amounts of matter and energy to keep passengers safe and maintain the correct passage of time. Plus, communication between people inside and outside the bubble would become super distorted during the passage through the curvatures of warp space. Now, of course, there are still tons of problems researchers need to deal with before finally building a working warp drive. But some of them claim that the model should eventually get close to the speed of light. But even if it remains below the speed of light, it'll still be a great improvement compared to our today's technologies. Hey, see for yourself. Traveling at even half the speed of light to Alpha Centauri would take 9 years. In contrast, Voyager 1, which is currently traveling at 38,000 miles per hour, would need around 75,000 years to reach our neighboring star system. There are some more things to consider. As you approach the speed of light, things get really weird. For example, the faster an object moves, the greater its mass becomes. And this mass can increase infinitely, so that the object will need an infinite amount of energy to maintain its speed. Another issue, current models allow a stable warp bubble only for a constant speed. But then, how are you supposed to accelerate at the beginning of your journey? And what should you do when you eventually need to slow down and stop? Experts claim that the process of the creation of the warp drive is like trying to figure out the concept of the automobile for the first time. We can compare the stage at which the warp drive technology is with the car technology at the end of the 19th century. At that time, automobile travel was possible, but it looked like a tricky process not everyone could deal with. Now, the whole warp drive idea is to stretch and squeeze space to zip around the universe. Well, there's a theory that's even wilder. What if, instead of bending space-time, we just ripped it? Think about it like this. When you bend space-time, you still have to deal with all the stretching and compressing. It's like folding a paper map. You still have to drag your finger across the folds. But try ripping the paper in half and slapping the two ends together. Bam! You're already at your destination. So, how can we rip space-time? We might not need to. Black holes may already be doing it. At the center of a black hole, gravity goes nuts. Everything compresses into an infinitely small point, and time itself stops. This point, called a singularity, might be that very rip in space-time. And if you could ride your spaceship into a large enough black hole, gravity might be smooth enough for you to survive the journey. Maybe. And then, some scientists think you might pop out the other side of the universe through a white hole. Okay. Now, another type of rip is called a wormhole. Unlike a black hole, wormholes have both an entrance and an exit. They're like a cosmic tunnel shortcut. If we could figure out how to find them, open them, and keep them from closing again, we could get the key to intergalactic travel. And now, get ready for a twist. Quantum tunneling. Now, let's say you're playing a video game, and your character can magically walk through walls. It's kind of what particles do in quantum tunneling. Particles can tunnel through barriers, even if they don't have enough energy to go over them, thanks to their wavy quantum nature. But what if particles could quantum tunnel through connected wormholes? Instead of just sneaking through a wall, they'd be taking cosmic shortcuts through space-time, zipping from one part of the universe to another instantly. In theory, this could open up totally new possibilities for how we understand the universe and travel across it.
Imagine you could travel through the universe by hitching a ride on space dust, meteoroids, comets, or even rogue planets. Wouldn't it be incredibly cool? This idea is known as panspermia. It has captivated minds for centuries, but despite its appeal, it hasn't gained much popularity among mainstream scientists. Mainly, it could be because it doesn't explain how life originated and isn't easily testable. At the same time, certain events have reignited interest in the theory, even among skeptics. And one of such events was the appearance of the mysterious Oumuamua in our solar system in 2017. Oumuamua was a mysterious object that zipped through the solar system at an astounding speed. It was the first interstellar object spotted passing through our star system and the first detected hyperbolic asteroid, an object with an orbit not bound to the sun. Observations indicated that Oumuamua was likely to be a highly elongated cigar-like object. Overall, it was a very unusual object. Scientists couldn't quite pin down what it was. Some of them suggested it was a comet, others bet it was an asteroid, and there were those who thought it might be a chunk of frozen hydrogen. In April 2020, astronomers presented a new possible scenario for the object's origin. According to one hypothesis, Oumuamua could be a fragment from a tidally disrupted planet. If true, this would make Oumuamua a rare object of a type much less abundant than most extrasolar dusty snowball comets or asteroids. What made Oumuamua especially interesting to those who support the panspermia theory is that it was a visitor from another star system, so it was possible that it could have carried life across the galaxy. The idea of panspermia advances 3 stages: escape from a planet, transit through interplanetary space, and landing on another planet. Therefore, the Oumuamua hints that panspermia is possible. Recently, a new study titled "The Implications of Oumuamua on Panspermia" has seen the light of day. It was led by David Tsao from Thomas Jefferson High School for Science and Technology, an intern at Johns Hopkins University. The study explored how many objects like Oumuamua might exist and what characteristics they would need to transport life safely across the cosmos. The researchers considered different types of space debris, such as asteroids and comets, and estimated their potential to shield life from harmful radiation, particularly gamma rays from supernovae. If these objects weren't large enough, the intense radiation would sterilize any microorganisms hitching a ride. According to their findings, space debris made of materials like nickel or silicate could provide sufficient protection. But for a passenger to survive, they would need to have a minimum size of about 21 feet. The study also tried to estimate how likely it was that extremophiles, organisms that can survive in extreme environments, could have been delivered to Earth in this way. They calculated that roughly 40,000 objects of at least 33 feet in diameter could have impacted Earth during its first 800 million years. While this number might sound like a lot, the chances that Earth itself was seeded by panspermia are extremely low, less than 0.001%, according to the study. Interestingly, the researchers didn't just consider Earth as a recipient of panspermia, but also as a potential source. If Earth or another habitable planet ejected life-bearing material into space, that material could, in theory, seed other planets across the galaxy. The study suggests that under optimistic conditions, up to 100,000 Earth-like planets in the Milky Way could host life as a result of panspermia. However, many factors remain uncertain. For instance, the number of rogue or free-floating planets in the galaxy could significantly affect the panspermia hypothesis. Hopefully, when we discover more about these planets and the overall density of interstellar material, we will understand more about panspermia. The scientists have also underlined that the conditions in the galaxy were different in the past. For example, during an event known as the Late Heavy Bombardment, the rate of impacts on Earth and other bodies in the solar system was 100 to 500 times higher than it is today. If similar events occurred in other star systems, the potential for panspermia would be much greater. Despite its allure, the panspermia theory remains a fringe idea in scientific circles, all because of the many unknowns and its speculative nature. But as we gather more data from projects like the upcoming Rubin Observatory's Large Synoptic Survey Telescope, which is expected to detect many more interstellar objects and rogue planets, astronomers will likely revisit and reassess this idea. A shocking theory claims that mysterious comet Oumuamua might be a von Neumann probe, an alien spacecraft with broken engines tumbling through our solar system. It sounds extremely unsettling, but first things first, what is a von Neumann probe? Mathematician John von Neumann suggested the concept of self-replicating spacecraft that could in some ways mimic the features of living organisms or viruses. People started to refer to such hypothetical spacecraft as von Neumann probes. Von Neumann was sure that using self-replicating spacecraft would be the most effective way to perform large-scale mining operations, like mining asteroid belts or moons. The creators of such probes could take advantage of their exponential growth. Hypothetically, a self-replicating spaceship could be sent to a neighboring planetary system and look for raw materials there. Such materials could be extracted from moons, gas giant planets, asteroids, and the likes. Using these materials, the probe could make replicas of itself. The replicas could then be sent to other planetary systems, and the original probe could pursue its main purpose within its parent star system. This pattern sure does repeat the reproduction patterns of bacteria. That's why some experts think that von Neumann machines could be considered a form of life. There's also a theory that a self-replicating spacecraft could spread throughout a galaxy the size of the Milky Way in just 500,000 years, even if it used conventional theoretical methods of interstellar travel. In other words, it wouldn't even need to employ exotic faster-than-light propulsion. In 1981, mathematical physicist and cosmologist Frank Tipler argued that extraterrestrial intelligence couldn't exist because people had never observed von Neumann probes. Even if we take a moderate rate of replication, such probes should already be common throughout space. So, it's really weird that we haven't come across any of those yet. It might only mean that extraterrestrial intelligence doesn't exist. A response to Tipler's arguments came from astronomers Carl Sagan and William Newman. They pointed out that Tipler might have underestimated the rate of replication, and von Neumann probes should have already started consuming most of the mass in our galaxy. Therefore, any intelligent race would avoid designing von Neumann probes in the first place and try to destroy any probes as soon as they found them. Another objection to the prevalence of von Neumann probes is that civilizations that could potentially design such devices have an extremely high probability of self-destruction before producing such a machine. In any case, the assumed capacity of von Neumann probes is unlikely in reality. But then, how about Oumuamua? These days, scientists are using high-tech scanners to examine a huge, cigar-shaped comet, which might or might not be an alien probe. One idea is that it's an extraterrestrial civilization spacecraft with broken engines wandering through our solar system. If that's the case, the object could easily be a von Neumann probe. Dr. Jason Wright from Penn State University thinks that a broken alien spaceship could move in exactly the same way as Oumuamua. Rather than moving through space like other space rocks, the 1,318-foot-long, 118-foot-wide space traveler is tumbling through the solar system. At the moment, it's traveling at a speed of around 200,000 miles per hour. In his blog, Dr. Wright says that if such derelict craft were not traveling fast enough to escape the galaxy, they could thermalize with the stars and end up drifting around like an interstellar asteroid or comet. They wouldn't have attitude control anymore and would eventually start tumbling. And it could distinguish them from regular interstellar asteroids. Plus, even though their propulsion was broken, their radio transmitters could work just fine. In any case, so far, it's just a theory, and further research is needed. What do you think? Is Oumuamua just a space rock or an alien space probe? The Black Knight, the mystery that won't let go. What if I told you that there is an object in space that defies explanation, an object that was not created by any space agency, has no official owner, and whose origin remains shrouded in mystery? You might think it's just another fantastic myth or a publicity stunt, but the story of the Black Knight will surprise you. You've probably heard about the Black Knight, A satellite that wasn't launched by humans but has been orbiting our planet for years. But how did it end up in orbit, and who is behind its creation? The answer to this question is hidden in the dark corners of space, and this enigma continues to haunt scientists. Signals from space, the beginning of the journey. Long before humans even thought about creating satellites, our world was already receiving signals from space. It all started in 1899, when the brilliant Nikola Tesla was conducting experiments on wireless energy transmission. In fact, he didn't just come up with ideas for future technologies, but also began to pick up strange signals that couldn't be explained by any earthly sources. This wasn't just static, this was a clear signal, which Tesla interpreted as a message from outer space. It was too strange to be a coincidence. But what was it? For a long time, scientists and researchers couldn't find an explanation. Ordinary radio waves, it seemed, couldn't have caused these signals. This mystical phenomenon marked an important milestone in the history of space exploration, but it still didn't provide any clear answers. Forgotten satellites and space paranoia. Decades passed, and by 1954, more strange reports began to emerge. During this time, amateur radio operators around the world began picking up unusual signals, seemingly coming from objects in Earth's orbit. Amid the Cold War, this sparked concern. If the Soviet Union could launch satellites, it meant the US should have been doing the same. But here's what was strange. No one knew about satellites moving along unconventional orbits. At this time, rumors started circulating about mysterious objects keeping watch over our planet. Some claimed these were satellites created by an unknown civilization. Others suggested they were just space junk, but none of the theories could explain the behavior of these objects. The Black Knight, the first glimpse. In 1960, the rumors intensified, and many experts began stating that Earth was being monitored by a mysterious satellite. Then, in 1998, during the STS-88 mission, astronauts accidentally snapped a photo while flying, capturing something that would be debated for years. In one of the images, a dark object was clearly visible against the backdrop of Earth. It looked like an artificial satellite, but its shape and structure didn't resemble anything we knew. This was too strange to be ordinary debris. Moreover, the object was clearly moving in orbit, not just some discarded space junk. For everyone who saw these photos, this dark object became the embodiment of a true cosmic mystery, full of unanswered questions. What was it really? There are many theories, but none of them offer a definitive answer. Some scientists argue that the Black Knight is an ancient satellite placed by an unknown civilization, perhaps even before humans arrived. This satellite could have been designed to monitor our planet, or serve some other purpose that remains unfathomable to us. It seems like it's from another era, another time. Others believe the Black Knight is an artificial object created by extraterrestrials. The theory that aliens might be observing us is nothing new. According to some researchers, this object could have been sent as part of a study of earthly life, acting as some sort of spy satellite to watch humanity. It might be part of a hidden project that's beyond our understanding. But there's also the more down-to-earth explanation. Some believe it's just space debris that accidentally ended up in Earth's orbit. But with each new photo and each new investigation of the Black Knight, this theory seems less and less likely. Why do we still not know? What's most surprising about this story is that, despite all efforts by scientists, we still don't know what the Black Knight actually is. Official agencies remain silent, and space agencies aren't rushing to share any information about it. Perhaps this is the greatest mystery of all. The Black Knight isn't just a satellite, but something more, something beyond our understanding. It might be a witness to ancient history, or a messenger from the future, observing our development. This object continues to inspire researchers, raise questions, and stir the imaginations of people worldwide. No matter what's really behind it, the Black Knight remains a living symbol of the mysterious and unexplored cosmos. We can only guess what it really is and what answers it holds. But one thing is certain, its mystery will not leave you indifferent. The future of the Black Knight. With each passing year, the mystery of the Black Knight grows deeper. Space missions continue to explore our satellite world, and scientists are increasingly discussing its origin. Who knows, perhaps one day we will solve this riddle. But until then, the Black Knight will remain one of the most intriguing objects in space. And maybe, just maybe, we will witness the moment when a new chapter of history unfolds in space. Perhaps this dark satellite will be the key that opens the door to a new world, a world we still don't understand.
We often hear about such threats as terrible diseases, natural disasters, or even an asteroid hitting Earth. These are serious dangers, and they're studied a lot because they could hurt us in the near future. But one threat that you don't hear much about is the expansion of the universe itself. While it's not something to panic about right now, it could be a big problem far down the line. Experiments show that our universe is constantly expanding. This expansion can be described in the following way. Imagine us as two ants sitting on a balloon that is constantly inflating. Then the distance between the two ants is constantly increasing. This process is called the expansion of the universe. A physicist named Dan Hooper from the Fermi National Accelerator Laboratory has been thinking about how expansion affects us. According to Hubble's law, the speed at which two objects are moving away is proportional to the distance between them. It means that the farther objects are, the faster they move away from each other. For very, very distant objects, this speed approaches the speed of light. In other words, there is a region of space that is moving away from us faster than the speed of light, which means it cannot transmit information to us. The boundary of this zone is called the cosmic horizon. It's the edge of the part of the universe we can see or interact with. Anything beyond the cosmic horizon is out of reach. And there could be all sorts of stuff there, galaxies, stars, maybe even other civilizations. But the universe is expanding faster and faster, and more galaxies are being pushed beyond the horizon. This means that over time, parts of the universe will disappear from view forever. What does it mean for the region we live in, which scientists call the local group? It's a collection of about 50 galaxies, including our Milky Way, that are gravitationally bound together. They're not moving apart like other galaxies because their gravity is keeping them close. These galaxies are on course to eventually collide and form a super galaxy within the next trillion years. But here's the catch. As the universe keeps expanding, all the galaxies outside the local group will eventually be pushed over the cosmic horizon. Hooper says that in about 100 billion years, everything beyond the local group will become completely unobservable and unreachable. So, the big question is there anything an advanced civilization could do to fight against this expanding universe? Before we try to figure it out, let's go back to an idea from the 1960s, when famous physicist Freeman Dyson suggested that advanced civilizations might try to capture as much energy as possible from their stars. He came up with the concept of a Dyson sphere, a giant structure built around a star to collect all its energy. If an advanced civilization built one of these Dyson spheres, they could use all the energy from their star to power their technologies and cities. Now, here's Hooper's twist on the idea. He suggests that advanced civilizations could build Dyson spheres that not only capture energy, but also move stars. The Dyson sphere would radiate energy in a specific direction, and this radiation would act like a kind of rocket, pushing the star in the opposite direction. Over time, these civilizations could gather stars and keep them close, preventing them from drifting beyond the cosmic horizon as the universe expands. But not just any star would work for this. Really large stars burn through their fuel too quickly, so they'd run out of energy before you could move them. On the flip side, really small stars don't produce enough energy to move quickly enough to stay inside the cosmic horizon. The best candidates are stars that are about the same size as our sun. They last long enough, and produce just the right amount of energy. Now, the fun part. If any advanced civilizations out there have already started gathering stars, we might actually be able to see it. Hooper predicts that these star-collecting regions could appear as massive areas of space, up to tens of millions of light years across, where most or all of the stars are surrounded by Dyson spheres. Of course, there are several big assumptions in Hooper's work. The first is that advanced civilizations would want to maximize their energy use. But maybe that's not true. Maybe they'll learn to live with less energy and not feel the need to gather stars. The second assumption is that the universe is expanding forever, and that this expansion is speeding up. While most cosmologists believe this is true, it's not a totally settled issue. Some scientists are still uncomfortable with the idea that the universe will keep expanding faster and faster because it seems to break some fundamental rules of physics, like the conservation of energy. So, if advanced civilizations aren't collecting stars, it might not be because they don't want to. It could be that our understanding of the universe is just wrong and the expansion isn't happening the way we think it is.
A Dyson sphere is a theoretical megaproject, a ginormous sphere encircling a star with platforms orbiting in tight formation. It's supposed to be an ultimate solution both for energy production and living space. The creators of a Dyson sphere get a lot of surface area for habitation and the ability to catch every tiny bit of solar radiation and heat produced by their central star. The first person to theorize about such a bizarre construction was British-American theoretical physicist Freeman Dyson. According to him, an intelligent extraterrestrial civilization could consider building this sphere after colonizing some moons and planets in their local stellar neighborhood. With the growth of their population, these aliens would need more and more energy to sustain their lives. Dyson calculated that assuming that this alien society grew at 1% per year, their area and energy needs would become 1 trillion times larger in a mere 3,000 years. And if their solar system contained a space body similar in size to Jupiter, they could take it apart and spread its mass in a spherical shell by building a structure at twice the distance between our planet and the Sun. This amount of material would be sufficient to build a huge number of orbiting platforms. Each of them could be 6 to 10 feet thick, which would basically allow this civilization to live on their star-facing surfaces. A shell this thick could be comfortably habitable and capable of holding all the equipment needed for using solar radiation without falling onto the star from the inside. But after absorbing all this solar energy, the sphere would have to re-radiate it. Otherwise, the energy would build up, eventually causing the construction to melt. It means that the light of a star wrapped in a Dyson sphere would look dimmed or even completely darkened, depending on how dense the platforms orbiting it were. At the same time, it would glow unusually bright in infrared wavelengths invisible to the unaided eye. Because of this infrared radiation, Dyson spheres are classified as a type of technosignature. It's a sign of activity that astronomers can use to discover intelligent life forms in the universe. Some Earth-based researchers have infrared maps of the night sky they examine in hopes of spotting Dyson spheres. So far, no one has ever found one. However, one study has selected several Dyson sphere candidates. Its authors have processed large amounts of information using a special data pipeline for combining and analyzing information. One of the main search criteria is the detection of excessive infrared radiation. At the same time, it's important to distinguish this radiation from that emitted by natural objects. After a complicated filtering of millions of objects, the researchers identified 7 potential Dyson spheres. Sure, further analysis is needed to determine their nature. To do this, scientists want to use optical spectroscopy, which may reveal more details about these objects and their origins. At the same time, the researchers admit that these candidate Dyson spheres might have other explanations, For example, they could be debris disks or protoplanetary disks of young stars. Only more research can show whether we can find traces of other civilizations among star systems. For now, it's still an open question. Interestingly, Dyson spheres have been spoken about a lot in science fiction. As far back as 1937, a novel called Star Maker by Olaf Stapledon described systems in one particular galaxy that were surrounded by a gauze of light traps, which focused solar energy for intelligent use. That was the reason why the entire galaxy was dimmed. In another novel, Ringworld, the writer spoke about a ring-shaped artificial structure surrounding a star.
Stop whatever you're doing for a moment and think about this. Where are we going? I don't only mean you or me. I mean our planet and the entire solar system. We've been traveling through space for eternity, but does this journey have any aim or destination? The solar system is moving at a speed of 450,000 miles per hour. Our beautiful blue Earth is snugly tucked inside it, and it seems that our region is quite calm and safe, not like some terrifying experiences our celestial neighbors go through. But where are we going? Just wandering around in a giant circle? Not really. Apparently, our galaxy, as well as several nearby galaxies, are being pulled toward a certain region of space. It's about 150 million light years away. The worst thing is that we do not know what exactly it is. That's why we call it simply the Great Attractor. This bizarre area is, unfortunately, on the other side of the Milky Way. That's why we can't see it. This region of the sky is known as the Zone of Avoidance, and it's part of why the Great Attractor is so mysterious. This zone lies in the general direction of the center of our galaxy, and there's too much dust and gas there for us to see far in the visible spectrum. But astronomers can see enough to understand that our galaxy, as well as nearby galaxies, are all moving toward the Great Attractor. It means that something must be making things hurtle in that direction. Could it be a gargantuan black hole hidden in the darkness of the cosmos, pulling things toward it and munching on them? Or is it something even stranger and more dangerous? What we know for sure is that this something is immensely massive. For the first time, evidence of the existence of the Great Attractor was discovered in the 1970s. At that time, scientists didn't have the needed equipment to see through the zone of avoidance. That region blocks most of the visible light coming from beyond. But the good news is that this gas and light can't block all infrared and X-ray light. So when X-ray astronomy became more powerful, people got the opportunity to sneak a peek at objects dwelling in that region. It turned out there was a huge supercluster of galaxies in the region of the Great Attractor. It's now known as the Norma clusters. This enormous structure, consisting of thousands of galaxies, has a mass of around 1,000 trillion suns. So, the Norma cluster is massive. That's true. And local galaxies seem to be moving toward it. And still, it doesn't explain all the movements in that region. And now, I'll tell you something even more puzzling and spooky. The mass of the Great Attractor, whatever it is, isn't enough to account for the pull. If we take an even larger region of galaxies, it will become clear that both the Great Attractor and local galaxies are moving towards something even larger. This space behemoth is known as the Shapley Supercluster. It's made up of more than 8,000 galaxies and is as massive as 10 million billion suns or even more. This supercluster is the greatest galaxy cluster we know about within 1 billion light years. And everything in the universe, Earth, the solar system, even the Great Attractor, are moving toward it. But at the moment, astronomers are still trying to find more information about the Great Attractor. The Hubble Space Telescope is now focused on the region of space where it resides. The largest galaxy visible in the region of the Norma cluster is ESO 137002. It's a spiral galaxy with large clouds of dust across the galaxy's bulge. Unfortunately, Hubble, being an optical telescope, can't see a tail of glowing X-rays extending out of the galaxy. And in general, observing the Great Attractor is difficult at optical wavelengths. The plane of the Milky Way both outshines and obscures with dust many objects located behind it. And even though we can get some information thanks to infrared or radio observations, the region behind the center of the Milky Way remains an almost complete mystery.
Even though it may seem that science has reached the level where there are no more mysteries left, it's not exactly true. And no modern physicist would dare to assume that our knowledge of the universe is near completion. What are scientists still wondering about? Let's figure it out. For one thing, dark energy keeps puzzling researchers even today, because the universe doesn't seem to add up. Even though gravity is pulling space-time, the very fabric of the cosmos, inward, the universe keeps expanding outward, and this process is speeding up. That's how the concept of dark matter was born. It's believed to be some invisible agent that counteracts gravity by pushing space-time apart. It goes like this. The universe expands, and more space appears out there, and with it, more dark energy. According to astronomers, this invisible energy must make up more than 70% of the universe. But no one knows how or where to look for it. Then there's dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Scientists call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. Its existence is inferred from the effects it has on visible matter, radiation, and the very structure of the universe. There are a few special detectors on the lookout for weakly interacting massive particles, of which dark matter might be composed. But so far, nothing has been found. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Then, there's the question of antimatter. It's the oppositely charged and oppositely spinning twin of good old matter. The intrigue here is why there is more matter than antimatter in our universe. It would be logical to assume that the universe would want to treat matter and antimatter equally. Thus, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced, right? Not really. If it had happened, there would have been a moment of total annihilation. Protons would have canceled antiprotons, electrons, anti-electrons, and so on. It would leave behind a lifeless, matterless expanse of space. Luckily, for some mysterious reason, when the universe was created, there was some excess matter. It didn't get annihilated, and that's how everything started. But there's still no accepted explanation for this. Then, we've got particle physics questions. They account for many unsolved problems. Sonoluminescence is one of them. Let me explain. Let's say you take some water and hit it with sound waves. It forms bubbles, low-pressure regions surrounded by high pressure. Once the outer pressure pushes on the lower pressure air, the bubbles collapse. But while collapsing, they emit light, even though the flashes don't last for more than a trillionth of a second. What bothers scientists is that it's unclear what the source of this light is. There are a few theories, of course. Some experts think tiny nuclear fusion reactions might be involved in the process. Others believe some kind of electrical discharge comes into play here. There's also the idea of compression heating of the gases inside the bubbles. None of these theories have been accepted yet. This might sound surprising, but we haven't figured out what exactly gravity is either. Other forces are mediated by particles, but not gravity. Some physical theories claim that it might be carried by a hypothetical massless particle called a graviton, but no one has seen these gravitons yet. We don't even know what kind of detector can be built to spot them. Even if gravitons come into contact with matter, and we aren't sure about it, they do it extremely rarely. There's also a theory that gravitons are closed loops of energy, but again, it's just a theory so far. There are tons of other unanswered questions bothering our minds. What happens inside a black hole? Is string theory correct? What is the fate of our universe? Do we live in a false vacuum? Hopefully one day we'll find the answers to all these mysteries.
Today, we're traveling to the ancient city of Abydos, within the famed temple of Seti I, where I'll show you something that will turn your world upside down. Apparently, people traveled by helicopters or some kind of other flying machines in ancient Egypt. But where could this advanced technology have come from? Perhaps from space. Let's start from the very beginning. Strange hieroglyphs were discovered on the ceiling in the ancient city of Abydos. Look at them attentively, eerily. They depict something that resembles modern or even extraterrestrial vehicles, a bit too much for it to be a coincidence. No wonder some people are sure that the Abydos carvings can serve as proof of ancient astronauts having visited Egypt more than 3,000 years ago. And the ancient Egyptian artists depicted their spacecraft in the carvings on the roof, support at the Temple of Abydos. These carvings have another name, the helicopter hieroglyphs. There is an opinion that these mysterious artifacts might depict 20th century technology, or technology developed in another star system, or even a different galaxy. Now, pay closer attention to this piece. Doesn't it remind you of a helicopter, or probably even a submarine? And here, we can clearly see two planes. Or is it a UFO? In any case, none of these machines existed at the time when the hieroglyphs were carved. If we look at this whole situation from this point of view, it looks like it supports the ancient astronaut theory, which claims that intelligent extraterrestrial beings, aka alien astronauts, visited our planet and made contact with humans in ancient and prehistoric times. In this case, the hieroglyphs could be the proof of this extraterrestrial contact in the past. Some ufologists are also sure that aliens were responsible for the creation of such famous monuments as the pyramids in Egypt and Stonehenge, along with many others. Now, many people have argued that the images uploaded to the internet are fakes. But no, they are in fact real. At the same time, Egyptologists have offered a more logical explanation for the carvings in Abydos. In ancient Egypt, it was common practice for hieroglyphs to be recarved and refaced over the years. This process, known as palimpsest, was often done when a new pharaoh came to power. That's why the new ruler's name was carved over the previous one. And we have documentary evidence that this did happen at the Temple of Seti I in Abydos, particularly during the reign of his son, Ramses III. One blogger, Hypnogogial, expressed frustration with what he sees as gullibility from New Age, UFO, Atlantis enthusiasts. He explained that the roof support carvings had been started under Seti I's reign and finished by Ramses II. As a result, where Seti I's name appeared, Ramses II's carving overlapped it, and vice versa. Over time, the erosion of these carvings, combined with the overlapping hieroglyphs, created the appearance of modern machines. But in reality, those unsettling images were kinda accidental. There are people who still question this scientific theory. They claim that if the carvings are simply the result of older hieroglyphs being covered up, the symbols should appear random and unique. Several sources, including the Arab newspaper Al-Sharq al-Awsat, published pictures from the Amun-Ra temple in Karnak, which show carvings strikingly similar to those found at Abydos. So, the supporters of the idea of the extraterrestrial origin of the carvings say that if those at Karnak are authentic, the palimpsest theory loses its credibility. But most likely, ufologists just see what they want to see, ignoring any scientific proof that goes against their theories. They don't want to accept the fact that erosion, as well as the phenomenon of overlapping hieroglyphs, could have easily happened at both historical sites.
Imagine you're staring at the night sky, just another ordinary evening, and suddenly a star blinks. Not just once, but in two quick identical flashes. Then silence. Nothing. For years. Until one day it happens again. Somewhere else. Another star, another double blink. No explanation. No confirmed pattern. No clear source. Welcome to the strange and captivating world of optical SETI, where we're not just listening for alien radio transmissions, we're watching the stars, and the stars might just be blinking back. More than 6 decades ago, the search for extraterrestrial intelligence, SETI, began with a project called Ozma. Frank Drake, the man behind the Drake equation, pointed a radio dish at a couple of sun-like stars, hoping to catch a whisper from across the galaxy. Since then, scientists have tried everything: radio, infrared, microwave, even laser pulses, to answer the same old question: are we alone? And while the answer has remained elusive, it's never been boring. Fast forward to today. Richard H. Stanton, a retired NASA engineer who's worked on legendary missions like Voyager and Grace, has been quietly running his own SETI campaign from the Shea Meadow Observatory in Big Bear, California. No fancy NASA lab, no billion-dollar budget, just a 30-inch telescope, a custom-made photometer, and thousands of hours of watching the stars. Stanton isn't listening. He's watching, and not just any watching. He's sampling starlight every 100 microseconds with a technique called photon counting. The idea? If someone out there is trying to communicate with laser pulses, brief, powerful blips of light, they might be visible, even across light years. And then came May 14, 2023. While monitoring a star called HD 89389, about 100 light years away, slightly bigger and brighter than our Sun, Stanton's system picked up something strange. Two fast, closely matched pulses of light, 4.4 seconds apart. The signal didn't look like a satellite, or a meteor, or a plane. It didn't match anything he'd ever seen. The star got brighter, then dimmer, then brighter again, all within 0.2 seconds. That's not typical stellar behavior, not from an object millions of kilometers wide, and not without a very specific cause. Stanton did what any good scientist would do. He tore the signal apart, checked it against known sources of interference, atmospheric noise, birds, satellites, cosmic rays. Nothing matched. Even more bizarre, when he compared the two pulses, the fine structure, the tiny variations in light between the peaks, was nearly identical. It was like the star stuttered, then repeated almost the exact same stutter 4.4 seconds later. And this wasn't the first time. Back in 2019, while observing HD 217014, also known as 51 Pegasi, home to one of the first exoplanets ever discovered, Stanton had caught a similar signal, dual pulses. At the time, he dismissed it, thought it might be birds or instrument noise. But now, with HD 89389 showing similar behavior, that's at least a possible pattern. And patterns, if confirmed, can mean everything. Then in early 2025, it happened again. A third event, a new star, HD 251, 81 light-years away. Two pulses, same structure. Three events, three stars, years apart. Yet all showing the same strange double blink. So what is it? Natural phenomenon? Some weird trick of light? Stanton isn't claiming it's aliens, and who could blame him? Science is full of false positives, but he's also not dismissing the anomaly. Because here's the thing, whatever caused these pulses, whatever modulated the starlight, it might not be coming from the stars at all. In fact, based on timing and structure, it could be closer, much closer, possibly even within our own solar system. Some possibilities Stanton considered include atmospheric refraction, maybe shock waves bending the starlight just right, or maybe some kind of object passed between us and the stars, diffracting the light. Could it be a satellite we haven't cataloged? An asteroid? Each explanation has problems. None fully account for what was observed. And that's the unsettling beauty of it all. We want answers. We crave explanations. But sometimes space throws a mystery in our face and whispers, "Not yet." Stanton's work is part of a growing interest in optical SETI, using light instead of radio to search for intelligent life. It's cheaper, faster, and in some ways, more precise. Projects like Laser SETI and Breakthrough Listen are also exploring this frontier, scanning the skies for patterns, flashes, anomalies. But Stanton's method stands apart. He's not sweeping the sky, he's locking on, one star at a time, watching like a hawk. And maybe, just maybe, that patience is starting to pay off. He's calling for more data, more eyes on the sky. He suggests arrays of telescopes synchronized across vast distances. If something is moving between us and the stars, these setups could reveal its speed, direction, even size. And if the star's light is being modulated without anything passing in front of it, well, that opens the door to a very different kind of question. As of now, Stanton isn't making wild claims. He's not saying it's aliens, but he's not saying it's not aliens either. And maybe that's the most honest answer we have. Because in the vast silence of space, it's the rare, unexplained pulse that reminds us someone or something might be out there, blinking, waiting, watching us back.
How is the death of the universe possible if the universe is infinite? The concept of the universe's death is more about its state and less about its size or infiniteness. Several theories predict how the universe could end, but they often focus on the thermodynamic properties, energy distribution, and the fate of matter over time, rather than the universe ceasing to exist entirely. Here are a few scenarios based on current scientific understanding: heat death or the Big Freeze. This is the most widely accepted scenario, based on the second law of thermodynamics. Over trillions of years, it's theorized that the universe will reach a state of maximum entropy, where all energy is evenly distributed and no work can be performed. The universe would be cold and dead, with all stars burned out, and every bit of energy spread out thinly across an ever-expanding cosmos. Big Rip. This theory suggests that the expansion of the universe, driven by dark energy, could continue to accelerate indefinitely. Eventually, this acceleration would become so powerful that it would tear apart galaxies, stars, planets, and finally molecules and atoms themselves. Big Crunch. The opposite of the Big Bang, this theory proposes that the expansion of the universe could reverse, causing the universe to collapse back on itself into a singularity. This scenario is less favored now because observations suggest the universe's expansion is accelerating, not slowing down. Big Bounce. This theory combines aspects of the Big Crunch with the idea of cyclic universes. It suggests that after a big crunch, the universe could bounce back and start expanding again, potentially leading to an infinite cycle of universes being born, dying, and being reborn. The concept of an infinite universe doesn't contradict these scenarios because infinity here refers more to the spatial extent rather than its lifespan or the distribution of matter and energy within it. Even in an infinite universe, the distribution of energy can become so even that no meaningful activity can take place, leading to a death of sorts in terms of the universe's ability to host life or undergo change. How can energy be distributed uniformly in an infinite universe? If the universe is infinite, then there must be infinitely many regions where energy is not evenly distributed. The concept of energy being evenly distributed in an infinite universe indeed presents a paradox when taken at face value. The idea primarily stems from thermodynamics applied to a more understandable, finite model of the universe. However, applying these principles to an infinite universe requires some nuance: local versus global uniformity. In an infinite universe, energy could become evenly distributed on a local scale, within observable regions, rather than globally. The observable universe, the part we can see and measure, might reach a state of maximum entropy, where energy within this region is evenly spread out. Beyond our observable universe, conditions could vary wildly, but those variations would have no effect on the state of entropy within our observable limits. The horizon problem. This issue is also related to the cosmological horizon problem, which the theory of cosmic inflation addresses. The horizon problem questions how parts of the universe are too far apart to have exchanged light, or any information, since the Big Bang appears to be at the same temperature. Cosmic inflation theory suggests that the universe expanded exponentially in a very short time period after the Big Bang, smoothing out any initial irregularities over a vast region. In this context, an even distribution doesn't necessarily mean perfectly uniform across infinity, but sufficiently uniform within the observable universe due to its rapid early expansion. The role of dark energy. The current accelerated expansion of the universe, driven by dark energy, adds another layer of complexity. If dark energy continues to accelerate the universe's expansion, it could lead to scenarios like the Big Freeze or the Big Rip. In these cases, while locally, within our observable universe, energy might become more evenly distributed as stars burn out and matter spreads thin, the global picture across an infinite universe might be far more complicated and beyond our current understanding. Theoretical limits. The discussion of energy distribution in an infinite universe touches on the limits of our current theories. General relativity, quantum mechanics, and thermodynamics are all based on observations and experiments within the observable universe. Extrapolating these theories to an infinite cosmos involves assumptions that may not hold universally. In summary, when physicists talk about the universe reaching thermal equilibrium or heat death, they're often referring to the observable universe. The concept of an infinite universe introduces complexities that challenge our current understanding, suggesting that the true nature of the entire cosmos could be far more intricate than our local observations can reveal.
A single brain filled with fake memories of having existed in our universe. Once, this brain just spontaneously formed in a void. Sounds like something from science fiction. But this brain could actually be me, or you. There is an idea that such a brain is more probable than an entire universe that came about in the manner cosmologists think it did. And this phenomenon I'm talking about is known as a Boltzmann brain. Let's see. A brain is coming into existence in our vast universe right at this second. And everything in this brain is forming at this moment. The memories of its previous life, obviously fake, its origin, its ideas, and the perspective of the universe. But this brain perceives itself as real. In this case, how will it know that its memories are artificial and its existence is no more than an illusion? This is what the Boltzmann brain paradox is about. It's the result of Ludwig Boltzmann's debate with other scientists on the interpretation of entropy. According to the second law of thermodynamics, the entropy, or disorder of a system, can stay the same or increase, but it can never decrease. Have you ever seen shattered glass return to its previous state? Neither have I. But Boltzmann stated that even though the probability of the entropy of a system staying the same or increasing is high, it doesn't mean that the probability of the entropy decreasing equals zero. This chance is just so small that it can be ignored. But everything changes when we speak about some infinite system. If such a system, for example a universe, has an infinite number of particles, there must be at least one possibility that these particles create something structured. Let's take an infinitely old universe. Such a universe means an infinite number of possibilities where the entropy increases, and a tiny chance of its reduction when particles come together and form a structure instead of existing randomly. So Boltzmann took this idea of an infinitely old universe and ran with it. He claimed that at some point, all those randomly organized particles the universe contained could come together and form a structured system. Maybe this formation of a structure even led to the Big Bang. One more idea he suggested was of a local system existing in an infinitely large system. It could be a universe containing structure and life and existing in the infinite system of a dead multiverse. Such a multiverse would have no structure, which is what high entropy suggests. And since we know that in an infinite system, there can be only one possibility of entropy reduction. All other universes except one would be dead. Interestingly, Boltzmann said that we don't need an entire universe or even a galaxy to confirm the existence of structure in a dead multiverse. The only thing we need is just one intelligent observer. And what part of the body is responsible for consciousness and cognition? Right, the brain. It could be a single brain randomly existing somewhere in a high-entropy dead universe, containing memories of its entire life. Scientists had to admit the legitimacy of this paradox, and still, everyone was sure they could never be a Boltzmann brain. Everyone knew their existence was not artificial. But that's exactly what a Boltzmann brain would think. After all, it wouldn't know that its memories and existence are fake. This realization caused quite a commotion in the scientific world. people started to research the probability of one being a Boltzmann brain. And it turned out that the existence of a Boltzmann brain in an infinite universe is way higher than the probability of a human brain. Statistically, we are more likely to be Boltzmann brains than real breathing creatures. But it's too early to fall into an existential crisis. Sure, there's no way to find out whether you are a Boltzmann brain or not, but there's a catch. Do you remember that we've been talking about a Boltzmann brain in the context of a universe which has existed for an infinite amount of time? But our universe hasn't existed forever. On the other hand, what was there before the Big Bang? Nothing? Or a dead multiverse where all the particles came together and caused the Big Bang, which led to our structured universe? Sounds uncomfortably close to the description of the Boltzmann brain universe. Imagine simultaneously being born, growing up, and getting old somewhere out there in the universe. Sounds bizarre and unrealistic. And still, according to the block universe model of the world, that's exactly what happens with you, me, and other living beings on our planet. It's as if someone drew pictures about every moment of your life and then just piled them one on top of another, creating a giant block of all things that ever happen at any time and at any place. The future, present, and past exist at the same time and are equally real. The block has 4 dimensions. 3 of them are spatial. It's length, width, and height. There's one more, time. To make it easier, let's picture our world as a cuboid, which is basically a 3-dimensional rectangle. Its height and width represent 2 of the 3 spatial dimensions of the universe. As for the 3rd spatial dimension, we'll replace it with time. At one end of the cuboid, we'll drop the Big Bang. And at the other, there will be the end of the universe. Let it be a big crunch. Our cuboid is filled with every single event that ever happens. Even this moment, when you're watching this video, exists somewhere in the block. Now, we perceive today as the present, yesterday as the past, and tomorrow as the future. From this perspective, it seems that time passes. But in the block universe, time doesn't flow. There's no specific present moment since the notions of the past and future are relative. You see, we are always located wherever we are, which means that everyone remains in the present. But the block universe theory doesn't deny the notions of earlier than and later than. These relations remain no matter what, and regardless of where anyone is located. For example, Molly the mammoth is located earlier than Marcus the tiger. This relation between Molly and Marcus will remain unchanged regardless of whether you're located later than Marcus or earlier than Molly. This way, in the block universe, now is any time you are located at. Past is any time or events that are earlier than your location, and future is any time or events that are later than your location. It sounds like in the block universe, we could travel in time since it's just another dimension. Well, it could be true, but of course, things just have to be more complicated than that. Traveling in time is way more difficult than traveling in space, but it's not impossible if you travel very, very fast. Traveling at extremely high speeds results in time dilation. We can travel into the future at a reasonable percentage of the speed of light, and to get to the past, we can use wormholes, shortcuts through space-time. But if we can travel in time in the block universe, can we change the past? Not really, because if you do, it'll create a contradiction. Keep in mind that, in this universe, the past is the same as the present or the future. What is past to you is future to someone else. And when traveling to the past, you're going to someone else's future. In the past, you'll act just like you do in the present, but you won't be changing the past. All your actions are already predetermined in the block universe. At the moment of the Big Bang, it's already clear that at one point, you'll travel to the relative past. Just like what you do tomorrow makes tomorrow the way it is and has always been, what you do in the past makes it the way it is and has always been. The events in the block universe do not change. As a time traveler, you don't suddenly appear in the past. it's always been the case that you're located in the past. And nothing a time traveler does can change anything in the block. Instead, whatever you do at any time makes that time the way it is.
The very first known interstellar object, or ISO, to pay a visit to our solar system was a rocky, elongated interloper with a slightly reddish hue. It was spotted in 2017 and was dubbed with the Hawaiian name Oumuamua. It was almost 10 times as long as it was wide, and it was extremely unusual. Objects in our solar system are rarely shaped this way, so astronomers hoped it could provide some clues into how other star systems form and function. For hundreds of millions of years, longer than I've been around, this bizarre guest has been wandering through our home Milky Way galaxy, not bothering to settle down in some star system. And then, it came across the solar system. After the space traveler was discovered, hundreds and probably even thousands of telescopes all over the world, including ESO's Very Large Telescope in Chile, sprang into action. They started measuring the object's orbit, its color, and brightness. That's when it became apparent that the space rock had an unusual orbit. Some astronomers suggested that Oumuamua was emitting hydrogen it had picked up during its journey between stars. This was a simple explanation for the mystery that had evoked lots of outlandish theories. When this bizarre guest was first spotted upon entering the solar system, scientists were not sure what its nature was. Some claimed it was a comet. Others disagreed, saying it didn't have the features typical for comets: a visible long tail and a coma, which is a cloud of gases surrounding the nucleus of a comet. Plus, its shape was different from that of other comets. The only thing that made Oumuamua more comet-like was the way it accelerated as it went away from the sun. The unusual object started to slow down on its way out, but in a strange way, as if not only gravity was in play there. It seemed like something was creating a force to counter this gravity. But unfortunately, this theory didn't quite fit either. The problem is that comets usually have large quantities of water ice on their surface, and as the sun heats this ice, it gets ejected as jets of gas. Those jets act as mini rocket boosters. But Oumuamua not only had no tail whatsoever, but it was also too small to capture enough solar energy to support this kind of activity. Of course, this mysterious space visitor caused some more outlandish theories. For example, some people started to claim that Oumuamua could be a spacecraft sent by a civilization living in another star system. However, scientists found a better explanation. A comet that is traveling between stars gets cooked by cosmic radiation. These rays penetrate thick layers of ice, converting up to 25% of water molecules into molecules of hydrogen. And then, this trapped hydrogen gets released when some star warms the comet. The effects of this process are almost invisible. This might be the reason why we didn't see a spectacular tail accompanying Oumuamua. At the same time, the potential comet was so small that this could produce enough force to power its acceleration. As for the amount of ice released as Oumuamua was coming closer to the sun, it was likely too small for astronomers to spot it. Now, even though Oumuamua was the first known interstellar object to enter our solar system, it wasn't the last. In August 2019, comet 2I Borisov visited us, becoming the second ISO astronomers managed to spot. Now, no one can argue that there simply must be more visitors from faraway star systems than those two. ISOs are rare, but our solar system is pretty old. It must have been capturing some interstellar travelers over the millions and millions of years of its existence, even though they never stayed for very long. One study has taken a closer look at interstellar objects, and they concluded that these space travelers might be caught not in solar orbits, but in near-Earth orbits. The astronomers working on this project even go as far as to claim that there might be a lot of ISOs in orbit around Earth. Now, finding tiny objects in the vastness of the cosmos is extremely tricky. Think about it. What images of distant areas of space do we usually get? Mostly stars. Sometimes unclear pictures of exoplanets. Even more rarely, it can be disks of debris. But fine detail in small space objects? Almost never. So it's actually lucky for us that other solar systems send their inhabitants to visit us. Because by studying ISOs, we gain insight into the formation, evolution, and functioning of other star systems. Have you ever heard of the Oort cloud? It's the most distant region of our solar system, and it's quite unusual. You see, the orbits of the planets lie mostly in the same flat disk surrounding the Sun. But the Oort cloud is believed to resemble a spherical shell surrounding the entire solar system. It looks like a gigantic, thick-walled bubble made up of chunks of ice and other space debris as large as mountains or even bigger. Astronomers think that the Oort cloud contains billions, if not trillions, of different objects. There might also be a connection between the Oort cloud and ISOs. Because scientists think that interstellar objects might outnumber those from the solar system in this region. Even though no one has ever observed the Oort cloud directly, astronomers are sure it does exist. They made such a conclusion after observing the distribution of comets in our solar system. The Oort cloud could have formed from debris in the early solar system, but some experts argue that the largest part of this unusual shell could be interstellar in origin. If travelers from other star systems are as common as some studies suggest, lots of the bodies on the edges of the solar system are likely to have originated in other systems. Sadly, this theory hasn't been proven yet. Now, since we've been talking about comets, not Cupid or Donder or Blitzen, one of them has recently approached the Sun at breakneck speed. It was 96P Mach-Holz 1. This comet is around 3.7 miles wide, and astronomers think it might have arrived from outside the solar system. The NASA European Space Agency Solar and Heliospheric Observatory spacecraft has been monitoring the comet. So look at this. That's the comet's tail. It's mostly made up of gas. It's trickling behind frozen chunks of ice that are getting heated by the radiation coming from the Sun. In some cases, a comet can have two tails, one made of dust and the other consisting of gas. And each of them can reach hundreds and, in some extreme situations, even millions of miles in length. In 2008, scientists analyzed the material left by 150 comets. They found out that the comet we're talking about was quite low in carbon and didn't contain a large enough amount of some other typical materials. This could only mean one thing. The comet was an interloper coming from another star system. It may have been ejected from its original solar system by the gravity of a large planet. After that, the poor homeless thing probably spent a large amount of time wandering around space, until it came across Jupiter. The gas giant could have bent the comet's trajectory, trapping it in orbit around the Sun. There's one more theory. According to it, the comet formed in a poorly studied region of the solar system, and it has this weird composition due to its repeated journeys around the Sun. Now, scientists are watching the comet with anticipation, like Christmas. Since it's an atypical one, both in its behavior and composition, they don't know what they will see, which makes the whole process even more exciting. Most comets falling toward the Sun are quite small, not more than 32 feet across. That's why they burn up as soon as they come close to our star. But the sheer size of Mach-Holz 1, which is more than 2/3 the height of Mount Everest, seems to protect the comet from evaporating completely. Voyager 1, which has been traveling through interstellar space for more than 45 years and is trailing a long gray beard by this time, not really, it suddenly began to send strange signals to Earth. Even more bizarre, there are no signs that the probe has broken or anything. Scientists from NASA are desperately trying to find the reason. So, what's happened exactly? First of all, let me tell you a bit more about Voyager 1 and its long journey. Voyager 1 is an American space probe. Scientists from NASA sent it into space on September 5, 1977. Voyager's goal was to explore the outer planets of our solar system, namely Jupiter and Saturn. Initially, scientists assumed that the mission would take about 5 years. Haha, the joke's on them. The probe exceeded all expectations. Not only did it fulfill its mission, but it's still working for much longer than expected. Voyager 1 has been wandering around space for more than 45 years. It's hard to estimate what Voyager 1 has done for science. Firstly, it successfully sent a lot of photos of Jupiter and Saturn to Earth. By the way, you can even check out these photos yourself. All of them are published on the NASA website. Thanks to Voyager, we also discovered several new moons of Jupiter and a previously unknown system of its rings. We learned that Jupiter's famous red spot is actually a giant superfast storm. And after leaving Neptune's orbit behind, Voyager also sent a lot of important data about interstellar plasma. So Voyager 1 successfully proved to scientists how useful it was. After that, it happily headed for its next goal, the Kuiper Belt and the heliosphere. The Kuiper Belt is a ring of icy bodies that extends from Neptune to a distance of approximately 50 AU from the Sun. It's kind of similar to the asteroid belt, but about 20 times wider and 100 times heavier. And the heliosphere is an area around the Sun where the pressure of the solar wind is balanced with the pressure of interstellar gas. Yeah, I know, it sounds like some hard scientific stuff. Just keep in mind that this data really helps us understand the universe as a whole. So, this is Voyager's last task, to tell us more about interstellar space. The probe has already sent us more than 60 frames for a mosaic of the solar system from a distance of over 4 billion miles from Earth. Scientists used these frames to make a big colored picture. The photo was called the pale blue dot, and you've probably already guessed what that dot is. Yep, that's what our Earth looks like through Voyager's eyes. This photo clearly shows how tiny we really are, and how precious and fragile our planet is. But Voyager 1 also has another, even more important mission, to tell other civilizations about us humans. You might have heard about the famous Voyager Golden Records. People created many audio and video files and added them to these records. There are a few sections. The first one contains hello in 55 languages, including ancient and extinct ones. Almost 80% of the recordings are different musical pieces, like Bach, Beethoven, Mozart, and Stravinsky, folk music from different countries and ages, and a bit of the blues, like famous songs by Louis Armstrong and Chuck Berry. The remaining 20% of the recordings contain different human voices, sounds of nature and animals, as well as 116 images encoded as audio signals. There's also recordings of speeches by Kurt Waldheim, a former UN Secretary General, and Jimmy Carter, a former US President. These are just some friendly messages. In addition to the records, scientists also packed a needle for playing them. Don't worry, they also left a simple drawing that showed how to use all this stuff and how to translate the sounds into pictures. They added Earth's coordinates, which they created using a pulsar map. It shows the position of the Sun in the Milky Way. The record was packed in an aluminum case and covered with gold to protect it against radiation and cosmic dust. Carrying this record, Voyager 1 set off on its long journey, and it has already traveled quite a distance, I'd say. Right now, Voyager 1 is 154 astronomical units away from us. That's about 14.5 billion miles. This makes it the most remote human-made object. Initially, this title belonged to the Pioneer 10 mission, but Voyager overtook it in 1998. What a bargain for NASA! It's way beyond its best-by date. Voyager 1 is actually so cool that it even overtook its twin brother, Voyager 2, which, by the way, had been sent into space 2 weeks earlier. Voyager 1 moves at a speed of 9.7 miles per second. That's 35,000 miles per hour. Even the fastest sports car in the world travels at a speed of only 305 miles per hour. So it's hard to imagine the speed of Voyager. Anyway, at the moment, Voyager is heading to the borders of the Oort cloud. That's the name of a hypothetical layer of icy objects surrounding the solar system. Astronomers haven't confirmed its existence yet, but they're almost sure it's there. After all, even black holes were only a theory not so long ago. Unfortunately, Voyager 1 won't return back to the solar system. It'll keep in touch with Earth at least until 2025. But eventually, we'll lose the connection with it for good. In 300 years, it'll reach the borders of the Oort cloud. And in 30,000 years, I won't be around then, it'll finally leave the solar system. And if nothing happens to it along the way, in another 10,000 years, Voyager 1 will approach red dwarf star Gliese 445 in the Giraffe constellation. In the future, the probe will probably keep wandering around the Milky Way galaxy. And now, let's finally discuss the mysterious signals part. So, what happened? Well, a rather unusual thing. NASA's Jet Propulsion Laboratory, which monitors and controls both Voyagers, reported this problem in May 2022. Our veteran spacecraft suddenly began sending strange data to Earth. The whole situation puzzles even engineers from NASA. Now, I bet you're thinking, come on, the thing just probably broke down or something. But the truth is that Voyager 1 is totally fine. It works as usual, receives and carries out commands from Earth, and collects and sends scientific data. But the readings of the AACS, which stands for Attitude and Articulation Control Subsystem, don't show what is actually happening to Voyager anymore. This system supports the orientation of the probe in space and helps it keep in touch with Earth. So, basically, the signals mean that the probe's orientation in space is messed up. But scientists claim this is not the case. They know that the source of the antenna signal remains in the same position relative to Earth as planned. The problem hasn't triggered any of the onboard fall protection systems. The probe hasn't even entered safe mode. So, what in the world, or universe, is going on? Suzanne Dodd, the head of the project, says that the problem is not actually that unexpected. After all, Voyager 1 is already 45 years old. The expert admits that what's happening to the probe remains a mystery to them. They don't know exactly where the incorrect data is coming from, and it's unclear how this will affect the operation of Voyager. She adds, though, that it's not that surprising, considering that the probe is in interstellar space. There's a very high level of radiation there. No spacecraft has ever reached that point before. Scientists from NASA say they'll keep closely monitoring the data coming from Voyager 1 until they figure out the problem. If they find it, the management team will try to fix it. Otherwise, the team will have to adapt to the new conditions. It might not be enough just to understand the problem, though. It takes as much as 20 hours and 33 minutes to receive the signal from Voyager, and it takes the same amount of time to respond to it. Well, at least the second spacecraft, Voyager 2, is totally fine, even though it's also currently in interstellar space at a distance of 12 billion miles from Earth. Anyway, we can only wait for news and hope that the problem will be resolved. I actually wonder how much longer can Voyager 1 last? Will it be able to fly to the borders of the Oort cloud in 300 years? What do you think? I'd like to hear your thoughts in the comments.
Weird, unusual sounds out of nowhere are spreading all over our galaxy, constantly repeating, and it's something we've never heard before. Scientists discovered it in 2020, and it was nothing like any of the other energy signatures they ever studied. Powerful and bright radio signals occurring from time to time, mysteriously disappearing within a day. It doesn't fit the profile of any space body we know. The signal is a bit irritating, and it disappears without a schedule. When scientists tried to match the signal with some other telescopes, it was gone. Low-mass stars sometimes flare up with radio energy, but not here, since they mostly have X-ray counterparts. Very dense collapsed stars, like pulsars and magnetars, are also not a choice. The closest solution they got is a mysterious class of objects we know as the Galactic Center Radio Source, GCRT. It's a radio source that brightens and rapidly glows. It decays near the center of our galaxy and could help us unravel the mysteries of the universe. If you had a flying car that could go up at a speed of 60 miles per hour, you'd only need 1 hour to get into space. The moon is a little bit farther, 250,000 miles, which is about 10 times the circumference of our planet. That means a moon trip would be like taking a tour around the globe and doing it 10 times straight, which would take less than 6 months. A trip to Pluto would take over 800 years. Proxima b is the closest Earth-like neighbor we have. It's a small rocky world that orbits the closest stellar neighbor of our Sun. It orbits the star's habitable zone, an area that's far enough from any star to have moderate conditions, not too cold and not too hot for liquid water to at least hypothetically exist. If you tried to travel to Proxima b at a speed of 25,000 miles per hour, which is the speed of the Apollo moon rockets, it would take you over 112,000 years to get there. You might not be able to breathe there. No one knows if Proxima b has an atmosphere. Humans explore the universe all the time, but we can only see around 5% of the matter up there. And Albert Einstein was the first one that realized the empty space is not really nothing. The rest we can't see is actually made up of invisible matter, also known as dark matter. It's about 27%, combined with something called dark energy, which is 68%. If you try to pour water into space, of course, outside of a spacecraft, it would immediately boil away or vaporize. That's because there's no air or air pressure in space. As air pressure lowers, the temperature you'd usually need to boil water at also gets lower. Keeping that in mind, water boils way faster on a mountaintop than, for example, at sea level. There's no air pressure in space, so water could boil at a very low temperature. Scientists believe that there are at least a couple of billion galaxies out there. We don't know the real number, and probably never will, but they tried to calculate it by counting how many galaxies we can see in a pretty small and restricted area of the sky. It may seem as if the universe was filled with stars and a couple of planets here and there, but our home galaxy has at least 100 billion planets. If you fill a balloon with helium and release it, you'll notice it floats very high. It'll go up into the atmosphere, but it won't go into outer space. The higher you go, the thinner the air in our atmosphere gets. Your balloon will rise up until the point where the atmosphere surrounding it has the same weight as the helium inside it. That will happen at approximately a height of 20 miles above the surface, so this is as far as a helium balloon can rise. We don't really know how big the universe is. We can't see its edges, nor do we know if it even has an edge. We use technology to see out to a distance of around 14 billion light-years from our planet. This means we can see around 28 billion light-years in diameter across, starting with the outermost layer of our atmosphere that ends at around 600 miles above our planet's surface. Although the size of the universe is constantly changing and gets bigger through time. Mercury is closest to the Sun, so most people think it's the hottest planet too. Still, Venus is the hottest planet. It's the second planet away from our central star, around 30 million miles farther from the Sun compared to Mercury. Mercury doesn't have an atmosphere, which is like some sort of a warming blanket that helps maintain the heat coming from the Sun. Venus has an unexpectedly thick atmosphere, around 100 times thicker than the one we have. Its atmosphere doesn't let the heat out, it just keeps it, and constantly makes Venus hotter and hotter. Also, it mostly consists of carbon dioxide that freely lets solar energy in. But it's less transparent to lose long wavelength radiations that the warm heated surface emits. The average temperature there is around 875 degrees Fahrenheit, which is hot enough to melt tin. The maximum temperature on its neighbor, Mercury, is 800 degrees Fahrenheit. In maybe 2 or more billion years, it will be way too hot for life to exist on our precious planet. As the hundreds of millions of years go by, our sun will keep getting hotter and brighter. Eventually, temperatures will be so high, our beautiful oceans will be wiped away. Since they produce 70% of the oxygen we need to survive, there'll be no life without them. All of this means that our planet will simply become a vast desert, something like Mars is today. Pluto, a very distant used-to-be planet, now dwarf planet, is actually smaller in diameter than the entire US. The biggest distance there, from Maine to Northern California, is approximately 2,900 miles, while Pluto is only 1,473 miles across. Pluto is very far, but the edge of our solar system is 1,000 times farther away than this dwarf planet. But astronomers found many space objects orbiting our sun way farther than Pluto, such as Kuiper Belt objects and trans-Neptunian objects. There's also an Oort comet cloud that goes half a light year from Pluto, also 1,000 times farther. A neutron star is really heavy. Just a teaspoon filled with it would weigh 6 billion tons. Neutron stars are something that remain from huge stars that have run out of fuel. The fading star explodes, and its core falls apart, but due to gravity, it forms an extremely dense neutron star. These stars typically have a mass of up to 3 suns, but the radius there is around 6 miles, because this is one of the densest things in our universe, at least that we know about. The universe has a color, and it averages to be some kind of beige, or as they call it, cosmic latte. It also has its own smell that reminds you of seared steak or hot metal. At least, that's something astronauts floating in space have said. If you want to build a spacesuit, get ready to work really hard. It takes 5,000 hours to make it and will cost you $1 million. A really good one will have 11 layers of material and weighs about 110 pounds, and it needs to be comfortable. You'll need more space in there because you grow up to 2 inches when in space. When you're floating around in space, Earth's gravity doesn't have any impact on you. That's why the vertebrae in your spine might expand and relax a little bit, which means you'll be maybe 3% taller. For 6 feet, it's about 2 extra inches. Oh, don't worry, it's not permanent. As soon as you go down to Earth, you'll shrink back down to your normal size within a couple of months. Space isn't the best option if you want to have a conversation with your friend, because up there, sound doesn't travel at all. Molecules there are so far apart that sound vibrations can't reach them, which automatically means they can't vibrate, so we can't hear them. Movies are not accurate with this. No one could hear you screaming in space, too. We kind of live inside our sun. The sun is not just that big hot ball of light located 93 million miles away from us. Its outer atmosphere is way bigger. It extends far beyond the surface we can see. Our planet's orbit goes through its tenuous atmosphere. The evidence is when gusts of the solar wind generate the southern and northern lights. That means, in some way, we live inside the sun. Not just us, other planets too, including distant Neptune. The heliosphere, which is what we call the outer solar atmosphere, extends to about 10 billion miles.